This video is going to cover Chapter 2, Section 4, which is called Complex Numbers. So it focuses a lot on I, the imaginary number, and all of the different functions that you can do with that. So the imaginary unit is I. It is a lowercase italicized I, which looks something like this, okay? And it's an imaginary unit such that I equals the square root of -1. And I squared would equal -1. So anytime we see a negative under a root, we can simplify that by pulling an I out of that root. There's two parts to complex numbers, the real part and the imaginary part. So standard form of an imaginary number is going to be written as the real part. So this is the number that does not have the I, followed by the number that does have the I, and that's the imaginary part. So you can see something like 2 plus 3i. This would be standard form. The number without the I is called the real part. The number with the I is the imaginary part, and the I always comes last. If there's no if there's no A, it's called a pure imaginary number. So if it was just like 3i, that would be called a pure imaginary number. So here's just a couple examples of complex numbers. Again, it would be broken down into A plus BI, where A is the real part and BI is the imaginary part. So in this example here, I know it's a little blurry, but that says -4 plus 6i. The real part's -4, and the imaginary part is just 6. In this one, 2i, the real part is 0, and the imaginary part is 2. And in this last one, it's just 3, which would be 3 plus 0i, or the real part being 3 and the imaginary part being 0. The equity of complex numbers simply just says that A plus BI equals C plus DI if and only if A equals C and B equals D. So if I have two complex numbers that equal to each other, then they are only equal to each other if the two real parts are the same and the two imaginary parts are the same. All right, so here's our first example. It just says express as a multiple of I. So the first one is the square root of -16. If I were to expand this out, it would be the same thing as saying the square root of -1 times 16, which is the square root of -1 times the square root of 16. And the square root of -1 is I, and square root of 16 is 4, and then we always put the I last, so it's 4i. You do not have to go through that step every single time. What you can do is simply take every time there's an I, take that I to the outside, or every time there's a negative, take that I to the outside. It will cancel out the one that's underneath, and then you would just square root the 16, making it 4i. The second example has 7i squared. So now it's the reverse. The I is already in the expression. This would be the same thing as saying 7i times 7i. Or 7 times 7, which is 49. I times I, which is actually I squared. And I squared is -1. So this is -49. All right, so what can we do with these complex numbers? The first and easiest is obviously the simplifying that we just did, then adding and subtracting complex numbers. So we treat I just as though it's a variable, just like it was an X. You can only add two terms that both have an I on them, and then you can only add terms that are both real numbers that don't have the I. You're just combining like terms here. So example 2 says perform the indicated operation. Labeled these as A and B. So A is subtraction. We distribute that negative just like we normally would. So this becomes 7 plus 4i minus 9 plus 5i. And then we combine the two real parts, 7 and -9, which is -2. And then the two imaginary parts, 4i and 5i. So this is positive 9i. And then again, standard form always puts the I last. For B, it's addition. So I can just get rid of the parentheses. 8 plus 17, which is 25, and then 3i and -7i, -4i. Okay, then we can also multiply with i's. So anytime you've got a binomial, you'll FOIL just like regular, except that when we see I squared, normally it was an X squared, we would have left it alone, but now we see I squared, we're going to replace that with a -1. All right, so perform the indicated operation. Let's look at A first. You've got two binomials, so we're going to FOIL this out. The first would be 3 times 6, which is 18. Outer, 3 times -2, -6i. Inner, -5i times 6, -30i. And last, -5 times -2 is +10. And then I times I is I squared. So we can combine our like terms here, -36i. And then I squared becomes a -1. That becomes -10. And 18 minus 10 is 8 minus 36i. Now let's look at B. B is 2 minus 3i squared. So this, again, we can't distribute an exponent like that. So we would just duplicate this, which would be 2 minus 3i times 2 minus 3i. And then first, 4, outer, -6i, inner, -6i, and last, +9i squared. So this becomes 4 minus 12i. This I squared becomes a -1, so that's -9. And I get -5 minus 12i. Okay, the conjugate of a complex number. So we kind of talked about conjugates before when we were dealing with if I gave you the root and you were finding the equation. But the conjugate of a plus bi is a minus bi. It's the exact same term, so the same real and then the same imaginary. The exception is that one sign is a plus in between and one sign is a negative in between. So the conjugate of a minus bi would be a plus bi. And when you multiply a number or a complex number by its conjugate, you get a real number. You eliminate out the I. So on the bottom here is just an example. If it was a plus bi and a minus bi and you FOILed it out, you get a squared minus abi plus abi minus b squared times I squared. The middle two terms would cancel out. The b squared would stay, but then I squared becomes a -1. And then I'd get a squared plus b squared. So this is actually a shortcut. When you're multiplying two conjugates together, you can do a squared plus b squared. So if I had 3 plus 2i and 3 minus 2i, the a is 3, the b is just the 2. So the shortcut here is 3 squared plus 2 squared, 9 plus 4, which would be 13. So you can multiply it all the way out. They will cancel out. Or you can use the shortcut, which only works on conjugates. All right, so here's the example 4. Write the complex conjugate of the complex number, then multiply the number by its conjugate. So let's look at A first. The first thing we want to do is just identify the conjugate. So if my initial one is 7 minus 10i, then my conjugate is 7 plus 10i. And then I want to FOIL it out. So I'm going to show you first the FOILing, and then we'll use the shortcut. 7 times 7 is 49. 7 times 10i is positive 70i. Negative 10i and positive 7, negative 70i. And then negative 10, that's a negative 100. I times I is I squared. So these cancel. And then I have 49 minus, this becomes a -1. So 100 times -1. That becomes 49 plus 100, which is 149. So had we used our shortcut, we would have done a squared, which is 7 squared, plus b squared, which is 10 squared. And it doesn't matter if I use positive or negative because I'm squaring it. And then it'd be 49 plus 100, which is 149. So remember, the conjugate doesn't take the I. That's why you use a plus instead. Or the shortcut, sorry. All right, so B, this time it's not in standard form yet. The first thing we'd want to do is rewrite this in standard form. So the I comes to the outside. This would be I square root 5. Or square root 5i. That's really the only time I'm okay with like the I being on the front, because some people make the mistake and put the I underneath the square root. It is not underneath the square root. So you can write it either of these two ways. Just make sure that I is not underneath the root. So if that's my original imaginary number, it would be 0 plus 5i if I needed the real part. The conjugate to that would be 0 minus root 5i, or just negative root 5i. So I don't need the 0. Root 5i is my original. Negative root 5i is my conjugate. So this time, if I did a squared plus b squared, that a is 0, so I'd get 0 squared, plus the b is the square root of 5. Square root of 5 squared is 5, and this would be just 5. If you multiplied it all the way out, I'd get root 5 times root 5, which is 5. One's positive, one's negative, so it wouldn't be negative. And then I'd have I times I, which is I squared. I squared becomes negative 1, and negative 5 times negative 1 is positive 5. So either way, you get the same answer, and you can use both and check. Okay, complex numbers and fractions. So because a complex number is a square root in the denominator, technically that's irrational and we can't leave it there. So to eliminate a complex number in a denominator, we rationalize by multiplying both the numerator and the denominator by the conjugate of the denominator. So for this, you'd see something like this. Divide and express the result in standard form. So if I look at A, I've got it I in the bottom, which is the same thing as having the square root of a negative number in the bottom. Can't stay that way. So I multiply by the conjugate. The conjugate of 5i is negative 5i. What I do to the bottom, I have to do to the top. So my numerator becomes negative 15i. And the denominator, again, you can use the shortcut a squared plus b squared, or you can just multiply these out. This would be negative 25i squared, negative 25 times negative 1, which is 25. And then you want to simplify that out. So both of these are divisible by 5. This would be negative 3 over 5. And then the I gets written last and to the right of your fraction. Okay, now we'll look at B. This time I've got an expression in the denominator. So I've got 7 plus 6i over 5 minus 9i. The conjugate of 5 minus 9i would be 5 plus 9i. And I multiply both the top and the bottom by that. So let's work through the top first. So 7 times 5 is 35. 7 times 9i is 63i. 6i times 5 is 30i. And 6i times 9i is 54i squared. So my numerator is 35 plus 93i. This is a negative one, so negative 54. Combine my like terms there, and I get negative 19 plus 93i. So that's my numerator. For the denominator, I can actually use a shortcut. So again, a squared plus b squared means 5 squared plus 9 squared, 25 plus 81, which is 106. So then you would always want to see if that could get simplified. If it can't, you'll actually separate that out. So it would be negative 19 over 106 plus 93 over 106i. And it looks like that. All right, so the principal square root of a negative simply says that for any positive real number b, the principal square root of the negative number negative b is defined by the square root of negative b equals I times root b. This is basically what we talked about at the very beginning of the lesson. If we had the square root of negative 49, this would be the same thing as saying I times the square root of 49, or 7I. The biggest thing you have to realize in this section is that you must first express the root in terms of I and then simplify. So if I had a negative 5 underneath and a negative 3 underneath, let's say, actually let me make that negative 5 so that we can keep it consistent. I cannot multiply out what's underneath first. So if I multiply out what's underneath, negative 5 times negative 5 is actually the square root of 25, and that's just 5. But that's wrong. I need to take the I out of both of these before I multiply. So I'd get I squared, and then square root of 5 times square root of 5 is that square root of 25. And this becomes negative 1 times 5, which is negative 5. So this is the correct answer, okay? Not this. You need to make sure that when you're looking at something that has a square root with a negative, that you take the I out first. So something like this. Example 6. Perform the indicated operation and then write the result in standard form. So same set of instructions. Now we're looking at the square root of negative 54 minus 7 times the square root of 24. So the very first thing I want to do is take out the I, making that a positive 54 underneath. Take out the I here, making that a positive 24 underneath. Now, I can't combine these yet because they're not both the same square root. So I'm going to see if I can break this down. So this would be 2 and 27, 3 and 9, 3 and 3. And then the factor tree rules is if there's a pair of numbers, that one goes to the outside, and then anything that doesn't have a match stays underneath. So I'd get 3I times the square root of 6. And then I want to do the same thing here. 2 and 12, 2 and 6, 2 and 3. This time, a pair of 2's goes to the outside, and there's already a 7 there, so I multiply all that together. Negative 7 times 2, which is 14I. And then 2 and 3, square root 6. And now they both have an I, and they both have a square root 6, so these can be combined together into 1. 3 minus 14, which is negative 11I root 6, or negative 11 root 6I. Again, either answer is fine with me. Just be careful not to put that I underneath the root. Okay, example 7 just takes it kind of a step further. It says perform the indicated operations, write the result in standard form. So again, same set of instructions. So A combines your multiplying and the I, or the negative root. So the first thing we have to do is take out that I, this would be root 7, square it, which means it's 2 of these multiplied together. And then you can FOIL it out. So 4 times 4 is 16, plus 4I root 7, plus 4I root 7, plus I squared times the square root of 7 times the square root of 7, which is 7. 16 plus 8I square root 7. That I squared becomes a negative 1, so that becomes a negative 7. And I end up with 9 plus 8I root 7, or 9 plus 8 root 7I. Either one would be good. If this was multiple choice or standardized, you'd see it on the bottom. This would be the answer. Okay, now let's look at B. So B's got negative 8 plus the square root of negative 48 over 4. So again, first thing I want to do is take out the I. I can't simplify it yet, but 48 is 2 and 24, 2 and 12, 2 and 6, 2 and 3. Each pair of 2's would go to the outside. That's 1. Second pair, that's 2. And 3 is the only thing left underneath. So I get negative 8 plus 2 times 2, which is 4, times the I, times the 3 that's left underneath, over 4. And then I can either split it and then reduce it, or reduce it and then split it. It doesn't really matter. If I split it first, I get negative 8 over 4 plus 4I root 3 over 4. And then 4 goes into 8 twice. These 4's cancel out. And I have -2 plus I root 3, or -2 plus root 3I. All right, this last example is using the quadratic formula. So we used it a little bit before the last test, but just a refresher, x equals -b plus and minus the square root of b squared minus 4ac all over 2a. So up to this point, everything under that root would have been a positive number, and now we're going to get i's. So a here is 4, b is 12, c is 15. I get -12 plus and minus the square root of 12 squared minus 4 times a, which is 4, times c, which is 15, all over 2 times a, which is 4. -12 plus and minus the square root of 144 minus, this is 16, times 15, or I can actually group it easier. 15 times 4, which is 60, times 4, which is 240. Divide that by 8. -12 plus and minus the square root of 96, -96 over 8. So as soon as you see that negative, the I should come out front. Square root 96 over 8. There is no square root of perfect square of 96, but this would be 3 and 32, 2 and 16, 2 and 8, 2 and 4, 2 and 2. And there's one pair of 2's, so a 2's going to go to the front. A second pair of 2's, that 2's going to go to the front. And the 3 and the 2 would get multiplied together underneath. So -12 plus and minus 2 times 2, which is 4, I root 6 all over 8, which is -4 over 8. I'm sorry, -12 over 8 plus and minus 4I root 6 over 8, which can get simplified to -3 halves plus or minus I root 6 over 2. And then that can be left as that, or you can bump the I to the end to be root 6 over 2I. So sometimes you'll just see it written as -3 plus and minus root 6I over 2, and you can leave it together like that. But if it's a standardized test or a multiple choice test, it's going to be written like that latter one, where it would need to get split and the I gets bumped to the end. All right, that's it for the notes for 2.4. Your assignment for 2.4 is open on Canvas and WebAssign. You can use the remaining time in class to start that, and then we will move on to 2.5 tomorrow. Have a great day.